Now we discuss about the behavior of real gases. What do you mean by a real gas? A gas which really exists is called a real gas. Remember, whatever we discussed so far was for an ideal gas. What is an ideal gas? An ideal gas which does not exist but it is ideal only. Whatever we discussed so far, kinetic theory of gases, then ideal gas equation, Boyle's law, Charles' law, Avogadro's law, everything is applicable only for an ideal gas. Now what we can do is, we will apply whatever we done so far for an ideal gas to a real gas. See, you are familiar with the pressure against volume curve for an ideal gas. From Boyle's law, the red line indicates the behavior of an ideal gas, which we saw earlier. As the volume increases, the pressure will decrease. This is for an ideal gas. Now, the same curve, if you plot it for the real gas, what you can see, these are the low pressure regions, very low pressure regions. These are very low pressure, while these are low pressure or moderate pressure, while this is high pressure. For the sake of convenience, we divide the pressure into three regions. These are very low pressure, while these are moderate pressure, while these are high pressure. Now, what you can show is, at very low pressure, the blue line merged with the red line. That means the real gas behaves ideally under very low pressure. But what you can see, as you go up, that means as you increase the pressure, the real gas deviates from ideal behavior. So there is a deviation from ideal behavior for the real gas as you increase the pressure. So this is the conclusion. Now we have to discuss about that deviation. In order to discuss how far the real gases are deviating from ideal behavior, we have a term called a compressibility factor. It is denoted by the letter Z. And Z is equal to PV by nRT, the usual terms. And since for an ideal gas PV equal to nRT, the Z value must be equal to 1, which implies an ideal gas. Z less than 1 or Z greater than 1 or deviation indicates real gas. Z less than 1 is called a negative deviation, while Z greater than 1 is called a positive deviation. Now here you have a curve of compressibility factor, which is Z versus pressure for various gases like nitrogen, hydrogen, helium, carbon dioxide, etc. Now if you look onto this curve, what you can see, so here on the y-axis you have Z, and while on the x-axis you have pressure, and you have a line over here you can see, and this is Z equal to 1, which mentions ideal gas. That means along this horizontal curve you have ideal gas. Now look onto this curve. A general thing, we consider the gas nitrogen. This is for nitrogen it is. So this is for methane, while this is for carbon dioxide. And you have whatever the gas may be, you can see the curves chart with the value of Z equal to 1. So Z equal to 1 at a very low pressures. Then as the pressure increases, what happens? Most of the gas shows negative deviation. So here you can see negative deviation. Then as the pressure goes on increases, what happens? It shows positive deviation. So all the gases, not all, most of the gases behaves in this way. Here carbon dioxide, methane, nitrogen are examples. All these are real gases, of course helium, hydrogen, etc. So most of the real gases behaves in this way. Under very low pressure, the value of Z is equal to 1. But Under low pressures, it shows negative deviation. The value of z is less than 1, but at high pressures, the value of z is greater than 1. And at very low pressure, z equal to 1, that is ideal behavior. At low pressures, that is here, the value of z is less than 1, which means negative deviation. At high pressures, the value of z is greater than 1, which means positive deviation. So this is the behavior. So we saw there is a deviation. Now the question is why the gases are deviating. What is the reason for the deviation of real gases? Now you can see there's another deviation, and this is the deviation you can see. Listen, deviation from Avogadro's law. Remember, according to Avogadro's law, 1 mole of any gas, whatever the gas may be, irrespective of the nature of the gas, 1 mole at SGP would occupy 22.414 liter. Clear? But look on to nitrogen, which is a real gas. What is the molar volume of nitrogen at SGP? It is only 22.405, which is less than the volume of an ideal gas according to Avogadro's law, which is 22.414. And for oxygen it is 22.394. For ammonia it is 22.084. So it is clear all the gases are deviating from what is so called the ideal behavior. Now in order to explain the deviation, you have see the reason for the deviation is this one. Listen, there are two faulty assumptions in kinetic theory of gases, and the two faulty assumptions are the volume of individual gas molecules are neglected. Each and every molecules, the spot we shown at the beginning of the class are the volume of individual molecules, they are neglected. And another faulty assumption is there is no intermolecular forces between the molecules. Listen, we just interpret these two assumptions much more clearly. Now you consider a vessel. Inside the vessel, suppose you have gas molecules, real gas molecules. Now suppose the volume of the container is decreased. Volume of the container is decreased. That by increasing the pressure, what happens? The volume of the container will decrease, but the volume of individual gas molecules will not change. So under high pressure, the volume of the container becomes small, that is volume of the gas, but the volume of the individual gas molecules are not changed. Now they are no more negligible. So the volume of individual gas molecules are no more negligible for real gas under high pressure. And similarly, see, you know all the real gases are liquefiable. Real gases are liquefiable only if there are intermolecular forces, isn't it? So if you take the ammonia gas, oxygen gas, nitrogen gas, all are liquefiable. But for an ideal gas, what we said is there is no intermolecular forces. But for real gases, there are intermolecular forces. So what we are trying to do? We are trying to apply the concept of ideal gas, that is kinetic theory, as such to a real gas. But it will not obey. Why? Because these two are not suitable for a real gas. The volume of individual gas molecules are neglected and there is no intermolecular forces. These two are not valid, because especially at high pressure, because as the pressure increases, as I said, the volume of the container will decrease. So definitely between the molecules will come more closer. If the molecule come more closer, there will be a considerable intermolecular forces. Clear? But this point to be noticed, A real gas obeys ideal behavior under low pressure and high temperature. Now, we come to a point. What's the main difference between an ideal gas and a real gas? The main difference is, for an ideal gas, there is no intermolecular forces. But for a real gas, there are intermolecular forces. That's the main difference we can identify. That means an ideal gas is not liquefiable, while real gases are liquefiable. Clear? Now we come to this point. Real gases obeys ideal behavior under low pressure and high temperature, because under low pressure the volume of the container is too large. Since volume of the container is too large, what happens? The molecules can move very freely and they can remain far apart. വളരെ ദൂരത്ത് നിൽക്കാൻ പറ്റും അവർക്ക്, because the volume of the container is very large. അപ്പോൾ മോളിക്യൂൾസ് വളരെ ദൂരത്താണെങ്കിൽ ഇന്റർമോളിക്കുലർ ഫോഴ്സ് ഓപ്പറേറ്റ് ചെയ്യുന്നത് ഒരു സർട്ടൻ ഡിസ്റ്റൻസിൽ മാത്രമാണ്. മോളിക്യൂൾ മേ ബി ബിയോണ്ട് ദാറ്റ് ഡിസ്റ്റൻസ് because the volume of the container is very large, so that there is no need of any intermolecular force. There may not be any intermolecular force. Clear? Similarly, if you increase the temperature, what happens? The intermolecular forces will break. So again, real gas behaves ideally. Clear? So real gas behaves ideally under low pressure and high temperature because no need to consider the intermolecular forces under these conditions. That's why they are obeying the ideal behavior under these two conditions. Okay, thank you.